here's the problem that we want to think about today. We want to find the slope of the line tangent to the function f of x equals 5 times the log of x when x equals 2. This is equivalent to asking for the instantaneous rate of change of the function when x is equal to 2. So this is like a speedometer reading for the function. Remember the issue that we have. Oh, here's the function y equals 5 log x. I multiplied by 5 so it would spread out a little bit more, and I don't have to change the vertical axis scale as much. So that's the only reason I multiplied by 5. All right. Remember that the issue is that we want calculating the slope needs 2 points, but we only have 1 point because we want the slope of the tangent line. So let's remember what the issue was. So recall. Slope formula wants 2 points. But a tangent line calculation, we only have 1 point. The slope formula wants 2 points, but we only get 1 point when we're trying to calculate a tangent line, or the slope of the tangent line. So the slope formula, slope is change in y divided by change in x. And we could think of this as y2 minus y1 over x2 minus x1. Need 2 points. If I try to plug the same point in twice, I get 0 over 0, and that's not defined. We cannot put a value on 0 over 0. Sometimes 0 over 0 is going to look like 0. Sometimes 0 over 0 is going to look like infinity. Sometimes it will look like something in between. That's why it can't be defined. So let's draw a picture of what we're going for. We got a point x1, y1. And we've got some other points, x2, y2. The delta y is how much things change vertically. So this distance is delta y. And this distance is delta x. Then we describe this direction by making a ratio of delta y to delta x. So what we're going to do is we're going to imagine these 2 points are on some curve. So if these 2 points are on some curve, and I want the slope at one of these points, what we're going to do is we're going to approximate the tangent line with a secant line so that we'll have 2 points. So since we need 2 points to calculate the slope, we're going to use a secant line as an approximation of the tangent line. That way, we'll have 2 points to work with. So now I'm going to translate this into, I'm going to look at this slope, change in y over change in x. I'm going to write it in terms of 2 points on a function. So let's suppose that I call this point, this is going to happen when x equals a. I think a is used in this book. So let's look at the point, this point is a, then the y coordinate is just going to be a plugged into the function. So a comma f at a. Now what we're going to do is we're going to look at a point close to when x is equal to a. So here's what we'll say. We'll say this point x2 is going to be a plus a little bit. And I'm going to say a plus h, where h is a little bit, just a small bit. That means a plus h is close to a. And then the y coordinate at this point is just going to be the function evaluated at a plus h. This plus h happens because we need 2 points to calculate slope, but we only got one. We only got 1 point to calculate slope, so we imagine a point that's close to the first point. We only have 1 point for our tangent slope. So we choose a second point near the first point. And it is h units away from a. H is just going to represent a small amount. This raises the question, how small of an amount? And the answer is just small enough. It just has to be small enough until we can figure out what we want. So if you're wondering how small is h, yeah, it's just small enough. And if you're wondering how will we know, we'll just know. So now the question is, how small should we make h? And the answer is small enough to find the information we want. How will we know? Eventually, we'll just know. That's why we do lots of problems. So I'm going to start building a table of values, and then we're going to start calculating some of these slopes. So I'm going to make a table of values with x and f of x. The point that we care about is when x is equal to 2. And I just need to calculate the log of 2, which according to my calculating machine is 1.505. Now I'm going to pick a value, a small value for h, and I'm going to get this, evaluate the function at that point, and then calculate the slope. So I'm going to pick an h of, let's say, 0.1. Let's choose an h to equal 0.1. So what we're plugging in is 2 plus the 0.1. So we started off here, a is equal to 2. And I'm going to choose a point that's near 2. So I'm going to take 2.1. I'm going to evaluate the function at 2.1. And it looks like we're going to get 1.611. Now I've got 2 points. And so I can calculate the slope. For an h of 0.1, our slope is going to be 1.611 minus 1.505 over 2.1 minus 2. So 1.611, oops, scroll up a little bit. It's down. So 1.611 minus 1.505, it looks like it's going to be 0.106. Divided by the 0.1. So 1.06. Now, some of you are thinking, Leach, that is way off. We know that the answer is supposed to be 1.0857. So we're going to have to pick a value of x that is closer to 2, because this doesn't give us enough information. So we're going to pick a smaller value of h, and we'll do the same thing. So I'm going to pick a value of h that's going to be closer to 2. So let's pick a value or closer to 0. That's the difference is what we're looking for. So let's pick a value of h that's equal to 0.01. So I'm going to evaluate the function at 2.01 and see what we get. So I'll go back to my graph. Oops. I'll go to my graph and I'll evaluate my function at 2.01. And so it's going to be 1.515. I'll call it 1.516. And then we'll calculate the slope again. So the slope is 1.516 minus 1.505 divided by 2.01 minus the 2. So here, when we calculate, we get the 1.516 minus the 1.515. We get 0.011, and we divide by 0.01. Now I think, man, things are getting worse. This seems worse, because now I've got 1.1. I'll go 1.1. 1.1 is as many figures as I get. So notice that we're looking at the difference between 1.516 and 1.505, and this 0.516 has been rounded off. So at this point, at 0.01, we might have to use more decimal places. So let's just go back and redo the problem. Instead of calling it 1.516, I'll use more places. 1.5159. Oh, I did 2. Yeah, I did 1.51598. I'm gonna go crazy with the decimal places. To reevaluate our function of 2, 1.50515. So we're just going to try this calculation again, but with more places. And we're also going to run out of space. Hold this. upside down the whole time. So I'm going to do 1.51598 minus 1.50515 over 2.01 minus 2. So our denominator is still going to be 0.01. And I'm not going to be able to subtract this. So 1.51598 minus 1.50515, 0.01083. Now when I divide by the 0.01, I end up with 1.083. So for those of you who were looking ahead and say, dude, just take the derivative and evaluate it at 2, you can see that we are much closer. That 1.1 came about because we had some rounding error. We were not looking close enough.
Professor.
Yes.
Could you talk briefly on how you got like the more specific numbers like 51598?
I just evaluated the function. So 1.51598, that's just the function evaluated at 2.01.
Oh, got it.
Going to be, this is f evaluated at 2.01 minus f evaluated at 2. I just used more, I just didn't round it as much this time.
Makes sense. Thank you.
So we can go even further, but what we want to, maybe what we want to do is to mechanize this process a little bit. So let's take a look at, let's see where, let's first find out where I put it. Here we go. Let me share my screen on a better graphing calculator. There it is. So here we have the curve we're interested in blue. So I've got 5 log x. And I'm going to make this calculation. Slope is the function at a plus h minus f at a over h. Notice that the h is just the same as a plus h minus a. So the h is the difference that we had before. So in the problem, in the calculations we made so far, h was first 0.1, then it was 0.01. And you can see in the graph in orange, I have the line containing the points 2.2, 1.505, and this point is very far away at 4, 3.01. And what we want to do is just bring these points closer together. So notice I'm decreasing the value of h, and we're seeing what happens to the slope of the tangent line. Now, the problem is when h gets down to 0, the slope is undefined because I'm trying to use the same point where I need 2 different points. Right now, we're looking at 0 over 0. So we're just going to plug in smaller values of h. Instead of 0.1, where we had a slope of 1.059, let's try 0.01, where we had the slope of 1.083. That's here in the with the 1.083. Let's try a different value of h, 0.001, 1.085. And if I keep adding more zeros, notice that more digits are just locking into my approximation. 1.0857, 1.085733, 1.085735, so that 3 is now locked in. Oops, won't do that. And the more digits that we include, the closer we put h to 0, the better our approximation is going to be. Because now the Desmos can not even distinguish between those 2 points. You can zoom in super far. And Desmos can no longer distinguish between the tangent line and the function. The closer h gets to 0, the closer we get to the closer the slope gets to tangent line, to the tangent line. The closer h gets to 0, the closer h gets to 0, the closer the slope of the secant line gets to the slope of the tangent line. Going back to the question of how close do these points need to be together, or how small does h need to be, that goes back to the h needs to be as small as it needs to be to find out the information that we wanted. So go back to the home screen here. At point 1, maybe I need the slope of the tangent line to be within the nearest hundredth. But we can see that at 1.059, if I change this to 0.01, I get 1.083. So now we want to make sure if this is the closest. If I go a little closer, it's 1.085. 1.0857. So it looks like that 5 is not going to change. 1.0857 again. 1.0857. So it looks like if we need it to the nearest hundredth, h needed to be to the nearest thousandth, because that's when we got a 1.08, or rounded 1.09. Oops. I accidentally deleted my tangent line. So we need to make h as small as we need to make it until we can find out the information that we want. In this case, we just needed more digits. Any questions? So to the nearest hundredth, it looks like the slope of the tangent line is 1.09. If we need this to the nearest thousandth, it would be 1.086. Here's the calculation that we're making. So the slope in general we are calculating a difference quotient. We're calculating the difference in the function close to f of a, and we're dividing by h. And we're saying that this is going to be the slope. Keep reducing the size of h until the slope is within tolerance. making m smaller until, or sorry, keep making h smaller until m is within the tolerance that you want. Any questions? So if we want m to be accurate to the nearest hundredth, h needed to be the nearest, h needed to be 0.001. If we just need the nearest tenth, h of 0.1 was just fine. Here are some of the things that we're driving at. This concept here, the closer h gets to 0, the closer the slope of the secant line gets to the slope of the tangent line, is what we want to try to quantify. Because what we're looking at is a limit. We need to make this idea rigorous by looking at limits. This notion that we're just going to make h smaller until m is where we want it to be, that's just fine for just calculations. But we want to make something more rigorous. We want to define what we mean when we say h gets closer to 0, the slope of the secant line will get closer to the slope of the tangent line. So here's what we mean when we talk about limits. And I'm going to write the definition. All you other professors that might be watching this video thinking, how could you start with the definition of a limit this early on in the game? I guess it's just madness. But we should get used to writing these things. Let's let f of x be a function. The limit of f as x approaches a is L, capital L for the limit, if and only if, or denoted. So we write limit as x approaches a. So you write x, then an arrow, and then a underneath limit, or lim for the as the abbreviation for limit. Limit as x approaches a of f of x equals L means. And now here's the definition of a limit. So the limit as x approaches a of f of x is equal to L if and only if for every epsilon greater than 0, there is some delta greater than 0 such that the absolute value of x minus a less than delta implies the absolute value of f of x minus L is less than epsilon. This is the epsilon delta definition of a limit. For every positive epsilon, there's a positive delta, such that the absolute value of x minus a less than delta implies the absolute value of f of x minus L is less than epsilon. That's what we mean when we say x minus, the limit as x approaches a of f of x is equal to L. Let's talk about what these symbols mean. Epsilon is how close we want f of x to be to L. Epsilon is how close we want f of x and L. This is what we're choosing. We choose epsilon to be the nearest 10th or the nearest 100th. I want f of x to be within epsilon of L. That's why we write it this way. We subtract the two, f of x minus L, that's the difference. We don't care if it's above or below, that's why the absolute value. Also, if it's negative, then it'll be trivially less than epsilon because epsilon is supposed to be positive. So we want the difference between f of x and L to be less than epsilon. So we choose the epsilon. That's the difference between f of x and L. Delta is how close x needs to be to A to guarantee that f of x is within epsilon of L. So the delta is how close x needs to be to A. Because when we write absolute x minus A, that's the difference between x and A. So the way we think about this is that L is the limit as x approaches A of f of x. If you can specify any tolerance, epsilon, and we can figure out how close x needs to be to A to guarantee that you'll be within epsilon of L. Over here is the difference. Limit as x approaches A of f of x equals L means for every epsilon greater than 0, there is delta greater than 0, such that the absolute value of x minus A less than delta implies the absolute value of f of x minus L is less than epsilon. That seems like a lot to remember, but only because it's a lot to remember, and you have to remember all of it all the time in perfect detail. And then you have to understand what we mean when we say it. You don't have to memorize the epsilon delta definition of a limit, but you do have to remember it always, all the time, in perfect detail. You don't get to leave stuff off. You can't paraphrase this. You say, limit as x approaches A of f of x equals L, if and only if, for every epsilon greater than 0, there is delta greater than 0, such that the absolute value of x minus A is less than delta, implies the absolute value of f of x minus L is less than epsilon. It is a lot, but we are trying to quantify, we're trying to make rigorous a very fishy idea. Oh, x is getting closer to A. What do we mean when we say x is getting closer to A? We mean this. This is quantifying where is this value headed. Any questions? This happens a lot in math. We want to describe something, and it just takes tons and tons of words to explain or to say what we need to say. It's why we invented algebra in the first place. When I ask what the Pythagorean theorem is, for the most part, I get a squared plus b squared equals c squared. I've gone back in time and checked. I'm like, well, hey, Pythagoras, a squared plus b squared equals c squared. He's like, well, what are you talking about? I'm like, well, that's how in the future we'll say the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And you'd be like, ah, you mean my theorem. And I'd be like, oh, dude, get over yourself. You know that idea is thousands of years old already. And his students would be like shocked. And he'll be like, oh, no, I came up with it. That's why it's named after me, Pythagoras. I'm just kidding. I have no idea if that's what it was like. Any questions? Comments? Snide remarks? All right. So tomorrow, I'm probably going to lead with asking you what the limit as x approaches a of f of x equals L means. And your answer will be, for every epsilon greater than 0, there is delta greater than 0, such that the absolute value of x minus a less than delta implies the absolute value of f of x minus L is less than epsilon. All you have to do is remember that. All of it. In that order. You don't get to start putting all this stuff out of order to try to make it seem different and like you weren't plagiarizing. It needs to sound like that. Any questions? Comments? Snide remarks? So this is going to be our next big thing. We're going to talk about limits and why we care about limits. It hasn't shown up in the homework yet, but it will. It is not bad that you don't recognize the symbols. So I'm introducing a lot of these symbols. The epsilon and delta, those are just lowercase Greek letters, at least the way that I write them. So switching over to the board. We have this symbol here is my lowercase epsilon. This is my lowercase delta. The rest are fairly common, greater than or less than, and then absolute value symbols. This is also a new symbol, limit, and then underneath it, x arrow a. This is limit as x approaches a of f of x. So that's a new symbol, but the rest is standard issue. All right, we're going to pause the video here for today and then take care of any other questions that you have moving forward. So at this point, before I stop recording, at this point in calculus, you may find yourself seeming very confused. If you are very confused right now, that is the correct answer. It's the first day, and I just dropped the epsilon delta definition of a limit on you. So if you're looking at this and thinking, oh my gosh, I don't understand what's going on, it is the first day. You're not supposed to understand what's going on. It would be really, really frightening if I just needed to say something once and everybody who heard me would just understand what I just said. We wouldn't have whole classes of calculus where we spend all this homework and all this time just looking at this one thing. I would just say it once and people would be like, oh, yes. But I think students get this idea that they hear a thing one time, then they're supposed to understand it right away. And that's just not true. And if you're feeling confused, right now there are 32 people in the room that are also feeling that same way. We also like to think that we're the only characters that are experiencing what we're experiencing. We also like to think that the camera is focused on you, and you look around the room and you think everybody else understands this. I'm the only one. I'm sorry, you aren't special. 32 other people do not know what I'm talking about. But there are 32 other people that have just taken their first step right along with you into knowing what the F I'm talking about. That make sense? So imagine this. I've hit a baseball before, like right on the numbers, went over the fence and everything. It was at least 360 feet. I smacked the crap out of it. You know what I can't do on a regular basis? Smack the crap out of a baseball. Part of it is, I mean, this is only partially correcting my vision problem, because only part of my vision problem is the roundness of my eyeballs. The other part is the way my eyeballs communicate with my brain. As stuff flies towards me, my brain's like, oh, no, this is too much math. I do not want to calculate with depth perception. And so I can see it coming towards me at about, and then about 30 feet away, it's like, oh, not 2D, it's all the same. And so I have no idea where it is. So it's a good thing I have some other skills. I don't know if teaching is one of them, but I'm really good at taking tests. Hasn't been really professionally useful. But for the most part, we have this weird idea about math. See it once and I should understand it, right? But then if we try to start learning a song on piano, we don't just try to play it once and it doesn't come out right, so we just give up forever. We allow ourselves to be bad at a song when we're first learning it. We don't allow ourselves to be bad at math when we're first learning it. So allow yourselves to not understand what's going on and start convincing it, start telling yourself that you've just taken the first step on the path to understanding, and all you have to do is keep going. Does that make sense? None of this is beyond you. I was talking to everybody in the room at that point. None of this is beyond you. You can get this. Take the time, allow yourself to be confused, practice, and move forward. All right, that's going to do it for today. I am going to finally pause the video, and if there are any other questions, I will stay online if you have some questions about anything else that needs to go on. So that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.